Yeah. So we shall start now. Welcome all. I am Dr. Punita Verma, and I'm written as a convener of this project. Science is organized knowledge and wisdom is organized life, said Immanuel Kant. Today, the 27th of July, is a day of history in our country, with no pomp and show, with no cameras rolling, and with no news channels covering this event. And the best of 30 professors and educators of our country from Delhi University have gathered under one umbrella organization of National Academy of Sciences, India, the Delhi chapter, under the patronage of our very, very respected Professor Ajoy Khattak, with just one desire in their hearts, that is to facilitate all the students whose love for science is authentic and genuine. This is a pioneer project which has the scintillating presence of eminent professors from Delhi University, whose wisdom is going to benefit all the thousands of participants who are right now viewing this event through a platform as well as through YouTube over a direct streaming link. And this program is going to run for a period of almost about 3 months. With blessings of Almighty and best wishes of all present here, let me invite our revered Professor Ajoy Khattak to give the keynote address. And prior to that, I request the co-convener of this project, Dr. Pushpa Bindal, to kindly introduce Professor Ajoy Khattak. Over to you, Dr. Pushpa Bindal.
Thank you, Dr. Punita Verma. It is a pleasant duty to introduce Professor Ajoy Khattak, who is an eminent physicist and, my best teacher till now. Professor Ajoy Khattak is currently Professor Meghna Saha Fellow of National Academy of Sciences, India. He received his PhD from Agra College, MSc from Delhi University, and PhD from Cornell University. He joined IIT Delhi in 1966. Professor Khattak has research interests in fiber optics and quantum mechanics. He has authored several books, including his undergraduate text on optics, which has been translated to Chinese and Persian. His other books include Quantum Mechanics, Theory of Applications, Fiber Optics, Lasers, and the most recent book on Einstein's Book of Miracles. He is recipient of 2008 Spy Educator Award in recognition of his unparalleled global contributions to the field of fiber optics research and his tireless dedication to optics education worldwide. The 2003 Esther Hoffman Beller Award, instituted by Optical Society of America in recognition of his outstanding contributions to optical education. The International Commission for Optics 1998 Galilei Award, and also the most prestigious CSIR 1979 S.F. Bhatnagar Award for outstanding contribution in physical science. In fact, very recently, he has been conferred another international award by Optical Society of America. Now, I invite respected Professor Khattak sir to say a few words, bless the gathering, and also introduce us to various activities of National Academy of Sciences Delhi chapter. Sir, you are invited to present your slide.
Thank you. Now I want to. You cannot start screen. I want to share my screen. Yeah, now I.
Yes, sir. Yes, sir. There is an option in green with the controls.
Yeah. Can you see the first slide?
It is.
Sir, it is sharing.
It is
So
starting.
it might be
it is sharing.
Okay.
Minute
Now
or
is it all right?
Sir, it is still sharing. It's coming.
Yeah. Okay. Thank you, Dr. Pushpa Bindal, for your very kind words. And thank you, Dr. Punita Verma, for inviting me to say a few words. So as you all know, these are lectures on learning physics with conceptual and problem-based approach. And it is organized by one of the hosts is National Academy of Sciences India Delhi chapter. I'm myself Ajoy Khattak, and I'm associated with the Delhi chapter of Sorry, I did switch off my cell phone, but just one second. Sorry, I'm sorry. So I thought that I should mention today, since there are a large number of students, that today is also the death anniversary of Dr. APJ Abdul Kalam. And there was a program that was organized by one of the colleges in Delhi, and in which I spoke on development of science in India. But I thought that Dr. Kalam was a great scientist and a technologist, a lot of reverence him on this particular date. So today is a very auspicious day. So the event is organized, as you all know, by Dr. Punita Verma. She has worked tirelessly towards the organization of this conference, of this 3-month workshop. She is the convener of this workshop, and Dr. Pushpa Vindal, both from Kalindi College. Dr. Pushpa Vindal has also worked very hard and has acting as a co-convener. We are grateful to both of them for taking all the efforts in organizing this very important workshop purely for the benefit of students, because of the COVID crisis, many of the classes have not been taken, and now we have floated this throughout the country. So throughout the country, people can listen to outstanding teachers teaching their subjects, and hopefully this will be of tremendous benefit to students and motivate them to generate some interest, greater interest in the discipline of physics. I'm going to speak a little bit about the National Academy of Sciences, which is the oldest science academy in India. And Professor Meghnad Saha was one of the founders. He was
Sir, your screen is not showing your slides of Nasi.
You didn't see anything?
No, sir, it's black.
Oh my
God.
No,
nothing. So, sir, while share screening, you have to choose a tab, or you have to choose, if it is on a Google Chrome, then a Google Chrome tab. Otherwise, you have to choose.
Is it now visible?
Dr. Poonam, please
No,
show
sir.
the exact. No, it is not. Please tell him
Sir,
the exact steps.
Yes,
shall I close this?
No, sir. Just a minute. I am stop your share screening. So now again, share your screen once.
All right. Yes. Can you see now?
No, sir. I cannot see still.
Just one second.
It is written.
Just one second.
Sure, sir.
Okay. Okay. Now, let me do it again.
Yes, sir.
Oh, sorry. ये तो हमारा चला ही है. ओहो. No. Sorry. Just wait. I'm sorry.
No problem, sir. No problem.
Oh, no. Let me log out, quit Zoom and come back again.
So while we wait for Professor Khattak to join again and renew his talk, I would like to share with you the real feeling behind, or the real motive behind this entire project. So as I grew up and was studying physics, I realized that a guidance of a teacher is very important for a life and career in physics. And as I used
Sorry
to
interrupt you, ma'am. Ma'am, sir has joined us again, and his screen is again visible to us. So,
Okay, so we shall continue with his talk first, and
yeah.
over to Professor Khattak to continue, please.
Thank you, ma'am. Thank you so much. Sir, now screen is visible to us. Ghatak, sir. Sir, kindly unmute yourself.
Oh, I'm sorry.
Yes, sir. Sir, yes, sir. Now it is perfectly fine, sir. Kindly make it in the presentation mode once.
Can you see now?
Yes, sir. It's perfectly fine.
Okay. So I mentioned that today is Dr. Abdul Kalam's birth anniversary, death anniversary. So we had a small program in one of the colleges. So we remember him, and this is for the students. He was a great scientist come technologist, and we all should emulate his sincere efforts for the development of this country. So they are the coordinators, as I told you. Can you see the photograph of Dr. Punita Verma and Dr. Pushpa Vindal? Can you see?
Yes, sir.
Okay, good. So they are the convener. Dr. Punita Verma has worked relentlessly towards the organization of this seminar, and at one point of time, I thought that it may be very, very difficult to organize this, but she has managed to do that. And Dr. Pushpa Bindal has also worked very hard as a co-convener. And both belong to Kalindi College. And as long as we have people like them, there is nothing to worry for the future of this country. That is true. And their dedication for the welfare of the students is really amazing. So I'm going to speak very briefly because we are already a little late, about the National Academy of Sciences India, which is one of the sponsors of this workshop. And it was founded by the outstanding physicist, Dr. Meghnad Saha. He was an outstanding scientist in 1920. This is 27 years before our independence. Meghnad Saha and Satyendranath Bose were the first to translate Einstein and Minkowski's paper on relativity. But what he is famous for is the Saha ionization formula, the degree of ionization of hydrogen or helium or that in the stellar chromosphere. So one uses the famous ionization formula to find out the degree of ionization of atoms in the atmosphere, in the stellar chromosphere and in the chromosphere of different stars. So it was an outstanding achievement, and he did it single-handedly in University of Calcutta. And for this particular work, he was nominated 6 times for the Nobel Prize. He was not only a great scientist, but also a great institution builder. And I would like to quote Dr. Mahendralal Sarkar, who said that the prevailing in 1869, he said that the prevailing backwardness of the country was due to backwardness of science, and that the solution was in the vigorous pursuit of the sciences by original research. And this is true even today, because we still have about 30% of our population, which is a staggering 400 million people, who are below the poverty line. And therefore, on 29 July 1876, he founded the Indian Association for the Cultivation of Science at Kolkata, supported by generous public contributions. In 1930, Professor Saha along with others, founded the Academy of Sciences with the objective to provide a national forum for scientific interactions and a forum for publication of research work. Professor Saha was the founder president of the Academy, now known as National Academy of Sciences India. And there are many, many chapters of that, about 23 now. And Delhi chapter is one of the 23 chapters of this particular academy. And the Delhi chapter sponsors a large number of workshops, science projects, and things like that. And so this is just one of them. And Professor Saha played a major role in making Allahabad University a world-class institution. He wrote a beautiful textbook on heat, which is still used for teaching the first principles heat and thermodynamics. He was the founder president of our academy. He established Positional Astronomy Center at Kolkata and was its first chairman. He started working on nuclear physics much before independence, and he created this Institute of Nuclear Physics, which has been named as Saha Institute of Nuclear Physics after Professor Saha's death. And then he created the Central Glass Ceramic Research Institute. So his contributions are really enormous. And then he, Professor, in 1935, 12 years before independence, Professor Saha and Acharya Prafulla Chandra Ray established Indian Science News Association and also the monthly periodical Science and Culture, with an objective to disseminate science news and also for public understanding of science and culture. Then in 1946, Indian Association for Cultivation of Science embarked upon a new development plan under the dynamic leadership of Dr. Saha, who prepared a master plan of the Jadavpur campus of IACs, which is now one of the premier R&D laboratory in our country. Professor Meghnad Saha was not only a great scientist, but also a great institution builder. Indeed, today, we require institution builders like Professor Meghnad Saha, Homi Bhabha, Vikram Sarabhai, Satish Dhawan, Shanti Swarup Bhatnagar, and many others. Indeed, he contributed so much to the development of our nation, and one cannot imagine what more he would have achieved had he not died at the early age of 63. So I thought I will say all this because the younger generation must be aware of the great scientists of our past, because of which we have made some contribution in science and technology. Today's speaker is Dr. Partha Goswami, who is Associate Professor of Physics at Deshbandhu College. He has worked extensively in condensed matter physics and has written a book on mathematical physics. So with that few words, I hand over this to my mic to Punita or Pushpa.
Thank you so much, sir, for this very good, precise, and wonderful introduction of NASI. And as I was filling the gap while you were trying to share your screen, I was sharing how this project got initiated, and I was sharing my own feelings while I moved as a student amongst JNU library books and the buildings with your book of quantum mechanics in my hand. From 9 o'clock in the morning to 12 o'clock in the night, I used to feel the requirement of a guidance of a teacher while you are preparing for any particular career in physics, whether it is just masters or whether it is research or whether it is teaching or any other research laboratory also. And over the years while teaching, I had my own alumni students and my own students who were facing several problems because some concept here or some numerical there was a source of an obstacle for them. And therefore started this initiative. I started this initiative first in my heart, and therefore this whole project has been sown few years ago, where I found my college students who were alumni and were in contact with me, who were suffering because they were not getting proper guidance in all the subjects up to the level that they required. And therefore I thought that during this COVID times, when all teachers have not been able to connect properly, we have not had classes, is the correct time to really engage ourselves in teaching and learning the whole syllabi of BSc and MSc. And therefore the candidates here, the participants here are BSc final year students who are just going to appear for the examination in Delhi University. However, the participants are not only from Delhi University, but are coming from but are attending this particular session from every state and city of our country, and we have left hardly any state untouched. These students of BSc passing out, that means they have already studied the BSc syllabus completely, and the ones who are pursuing MSc and the ones who have completed MSc and are on the threshold of developing a career in physics, they need guidance, they need our support, and a teacher is the one who is always available. This is the idea, this is the feeling that I want to give to my students. I alone cannot teach them all, and therefore I've done this mega project in order to collect the teachers from every corner of our university, every college. Invitation has been open to all to come and deliver lectures of their expertise and enlighten our students regarding the syllabus matter with complete focus on the concepts and the problem solving approach. Because only when the concepts and the problems solving approach is there embedded into our mind, the career in the physics can be built in this way or that way. So this was the feeling, and with which I have labored, and I'm extremely grateful and I'm extremely thankful to every human being who has said yes to my work. And I'm grateful and thankful to all the professors of Delhi University, who have agreed to contribute into this project, and all the teachers of various colleges of Delhi University who have contributed into this project. So we continue with our beginning portion. I request now Professor Dr. Pushpa Bindal to kindly introduce Professor Anurak Sharma sir, who is also our very, very respected teacher of and a member of RASI. Madam, please introduce Professor Anurak Sharma.
Welcome, Professor Anurak Sharma. He is my respected PhD supervisor. He has taught me in MTech and PhD both. Now I would like to give a formal introduction to Professor Anurak Sharma. Professor Anurak Sharma is an emeritus professor of physics department, IIT Delhi, where he has studied and has been working since 1978. He is an outstanding academician conferred with endless count of awards and fellowships, including the very latest J.C. Bose Fellowship and highly prestigious Shanti Swarup Bhatnagar Award. He has served as head of Department of Physics and Dean at IIT Delhi. He has authored a book on numerical modeling and has huge number of international publications in reputed journals and conferences. He has guided a number of PhDs, including mine. He is a fellow of all Science Academies of India and is secretary to the Delhi chapter. I welcome you, sir. I request you to say a few words of encouragement to our student participants. Professor Anurak Sharma.
Okay, good afternoon, everyone. Thank you, Pushpa, for these kind words of introduction. And I congratulate Dr. Punita Verma and Dr. Pushpa Bindal for putting up such a program, which is really the need of the hour, because students are kind of disconnected with formal education at the moment because of the pandemic that is going on. And this kind of course will be extremely useful and will kind of reconnect them to the teachers and to each other also. This kind of platform, which the kind of thing that has been thought of is really good, that you focus on concepts and then do problem solving, because problem solving is something which students generally skip over, and the concepts don't become clear. But unless you apply them, you cannot be clear on how to use those concepts. And this kind of platform which you're using, I mean, these days we have been forced to use this platform. We have been avoiding to use these kind of platforms all this long, although these were around. But this pandemic has really forced us into this, and it has several advantages. And I hope those advantages will be put to use. For example, of course, as I can see here, there are 440 participants at the moment. Now, this kind of classroom experience can never happen in a physical classroom.
So there are 1,500 participants watching you right now.
Okay, I can see on the screen.
Sir, they are on YouTube
Yes,
live.
YouTube,
They are
okay.
YouTube on your YouTube
right.
live.
That's right, quite right, correct. Thank you for correcting me. And then the other advantage of this platform is that actually you can show any video, any animation that you have ready. I mean, doing that kind of arrangement in a physical classroom is very difficult, not possible everywhere, of course very expensive. But now here things are very easy. You can switch to easily to a screen sharing mode where you can have a program running, you can have animation going on, you can have a video going on. This is extremely useful. And and you can actually this is what I understand, that the teacher is available to the participant or the students all the time. You can connect back, you can discuss with the teacher, you can send the question, and that question can be answered to all, and so on. So this is really a wonderful arrangement, and I'm sure it is going to work out very well in the next 3 months. This will also give experience to the teacher. Not only it will be beneficial to the students, but also teachers, because this is the technology which is going to come, which is going to stay even beyond pandemic, whenever that is. So and sort of even if you go to the physical classroom, the experience will give us kind of impetus to the use of this IT for our teaching, supplementing our teaching. So it's really a good idea, and I wish every success and great success to this program. And Punita and Pushpa, all the best for your program.
Thank you, sir. Thank you so much.
Thank you so much, sir. It is indeed a pleasure to hear you even for a minute. And this is another reason why we implore you, we request you to be kindly be present when we start a beautiful feeling of ours translated into action through this particular project. We are really grateful, sir. And now I would thank a very important organization that is Indian Association for Physics Teachers, which is well known to all the physics teachers of our country, a vast organization of which I also am grateful and I'm also proud to be a member of. Professor Vipin Srivastava, the president of the regional chapter of Delhi, could not be present, and he has requested Professor Ravi Bhattacharya to kindly join us while representing Indian Association for Physics Teachers. And we now, for this beautiful initiative, request Professor Ravi Bhattacharya, who is known to almost every physicist of our country. Everybody knows Professor Ravi Bhattacharya, who has only recently retired from Khalsa College, Delhi University, and has been involved in IAPT activities since time immemorial for me. I request Professor Ravi Bhattacharya
Dr.
to
Punita,
kindly,
Dr.
yeah, yeah,
Punita, Dr.
yeah.
Punita, I would like to say a few words about Dr. Bhattacharya before
Yes, yes,
we
yes, yes.
formally
I was
speak.
coming to that. I was
Yeah, yeah.
coming to that. So, Dr. Pushpa Bindal, kindly few words about our very
Yeah,
respected Professor Ravi Bhattacharya.
yeah.
And I seek, through him, I seek the blessings of IAPT for this initiative, because after all, physics is encompassing, it is nature, and it includes every organization which is propagating physics in our country. Thank you. Over to you, Dr. Bindal.
Professor Ravi Bhattacharya, welcome to you. I would like to say a few words about Professor Ravi Bhattacharya. Professor Ravi Bhattacharya retired from Khalsa College of Delhi University recently. He is coordinator and organizer of Asian Physics Olympiad India. He is also secretary of IAPT and also EC member of Central IAPT India. He is also associated in organizing many programs and events of IAPT. I welcome Professor Bhattacharya. I welcome you, and I request you to say a few words of encouragement to the audience.
Well, I was just not ready for this. Let me make a correction, right? I was the secretary of RC1 quite some time back. I'm no longer the secretary, but I'm of course associated with the activities of RC1 whenever it happens. Now, well, this is a very ambitious idea. I think this is the first time I heard from Punita and about this. About the goals of this workshop, and I think it is a very, very ambitious idea, and I'm sure she will have a very interesting set of resource team who will present their whatever is their field of expertise and lead students to some problem solving from there. So wish you all the best. Okay, thank you very much.
Thank you. Thank you.
Thank you. Thank you so much, sir. Without the blessings of IAPT, I would have felt out of place also. So through you and through Professor Ved Srivastava, sir, we take the blessings of IAPT for this nice initiative. And now I would request Dr. Pushpa Bindal to kindly introduce our speaker for today, Professor Dr. Partha Goswami, sir. Yes, madam, over to you.
Uh, Please share the slide, Poonam.
Yes, ma'am, doing it.
So as the slides come up for the information of the panelists, I would like to inform you, sir, as has been also clear from the poster, we have teachers from Delhi University, where we have professors from Delhi University, and we have teachers from various colleges. The plan has been to include one subject per week. However, at present, because of the coming examinations of Delhi University and the large number of students who have enrolled from there, we are going to continue till the 9th of August and then there shall be a break from 10th of August onwards for exactly 1 week. But for till the 9th of August, we would be covering up subjects like classical dynamics completely at the BSc level. We shall be covering statistical mechanics and also electricity and magnetism, electromagnetic theory. And after 20th August, we shall be continuing with coverage of all syllabi, and it will be held at 2 levels. So far, we will announcing that today is the revision of the BSc concepts, and then at the master's level and so on. Yeah. Okay. Over to Dr. Bindal for Dr. Partha Goswami's introduction.
Okay. So now I welcome our speaker for the day, Dr. Partha Goswami. Dr. Partha Goswami is MSc, MPhil and PhD from University of Delhi, and he is currently an associate professor in physics in Deshbandhu College, University of Delhi. He has done his graduation with first position from St. Xavier's College, Ranchi. He has been teaching mathematical physics to BSc Physics Honours students for past 30 years. His area of specialization is condensed matter physics. That is the theory part. He has 26 research papers to his credit, mostly under sole authorship, published in prestigious journals of physics. So I welcome you, Dr. Partha Goswami, and I invite you to deliver your talk. Please come on board. Varsha, you can start sharing.
Yeah. Thank you, ma'am. Thank you, ma'am, for your kind words. Am I audible?
Yes, you are audible.
My distinguished professors and my colleagues, I think it is a very rare privilege that I have to initiate this process in this mega project. So my thanks goes to Dr. Punita Verma. She had thought me competent enough to handle this job. So special thanks to her. And of course, thanks to everybody. So let me now get to what I have to speak about. Today, I would start with a special theory of relativity. I will not delve into very details of it, but whatever is required for BSc level, I would try to summarize in 26 odd slides, which I have summarized. The topics are space-time diagram of moving object, time dilation, length contraction, for velocity, for acceleration, for momentum, for force, and of course, linearity aspect of Lorentz transformation. So these are the things I would discuss, and I would use tensorial notation. One need to have a little concept of covariant and contravariant tensors to understand what is going on. So could you give project the second slide, please? Okay, in the second slide, I have summarized the postulates of special theory of relativity. The number one postulate, of course, is the principle of constancy of speed of light, and the principle has its origin in the negative result of the Michelson-Morley experiment, which probably was the greatest experiment of the 19th century. It was performed, and in fact, this experiment was performed at many places in different times of the year, but always stubbornly this experiment yielded negative result. We all know what was expected, some kind of friendship was expected, but that never had materialized. So it required the genius of Einstein to explain that if there is the friendship idea was arrived at assuming that the speed of light or velocity of light gets added in a usual manner as any ordinary velocity. So Einstein suggested that the velocity of light has to be put in a very different pedestal. It has, if I add any velocity to velocity of light, I should get back the velocity of light. And that kind of proposition ultimately led to no fringe shift, and which explained the outcome, the negative outcome of the experiment. Uh, I also would like to state in brief a little about what is inertial frame. An inertial frame is, of course, a frame at rest or frame in uniform motion, but there is no absolute rest. So frame moving with uniform velocity could be regarded as an inertial frame. A non-inertial frame, however, is a frame which is accelerating. And in fact, at the Galilean relativity level itself, we see that in the non-inertial frame, Newton's second law gets greatly modified. We have the pseudo force which is observed by non-inertial frame observer. So the first postulate, therefore, was principle of constancy of speed of light, and the second was that all inertial frames are equivalent. In fact, physical laws would hold in the same manner in all inertial frames. By performing any sort of experiment, one cannot make a distinction between the state of rest and the state of uniform motion. So these were the basic postulates. I believe my students who are hearing me out are able to make out what I am saying, or am I a bit fast? Yes? Hello?
Sir, they can reply only on the chat box.
Okay.
So I request the students, if you find the speed of the lecture a bit fast for you, kindly write down on the chat box immediately. So, sir, they are saying that so it's probability, somebody is finding it perfect, somebody a little bit fast. So you can probably decrease by a few steps, so that most of them
so
are
that
finding it fine. Some of them are finding it a little bit fast. So probably you can regulate a bit as per your liking.
okay. That's very good.
I think speed is fine, sir.
Yeah. What is it? Hello?
Speed is fine, sir.
Okay, it is fine. Okay.
It is absolutely fine.
That's good. That's good. I am gratified. Well, now I think all of us are familiar. I wouldn't go into that Galilean transformation. I have, suppose, two frames. One is at rest. Well, there is no rest. All right, but anyway, let's assume for the moment one frame is at rest. S, we call it as S. The origin is O, and there is another frame. Please go to the third slide. There is another frame, which is, please go to the third slide. Hello, please go to the third slide.
Yes, sir, I'm doing.
Varsha, please go ahead.
Yes, sir. It takes just 1 second time because of the delay in showing it.
Yeah. So, as I was saying, one frame is at rest, origin O, and there is another frame which is moving along x-axis with a uniform velocity. Let this frame be S dash and the origin be O dash. And we all know that suppose we have some particle in the space, three-dimensional or whichever, xy plane, let us say we are talking about, or xt, whatever. X dash, a particle, suppose, is in the space or plane with respect to the origin O. The particle has coordinates, suppose x, y, z, and with respect to the moving frame, O dash is the origin. the coordinates are x dash, y dash, z dash, and they are related, as all of us know, in the usual fashion: x dash equal x minus vt, y dash equal y, z dash equal z, and t dash equal t. This is what your Galilean transformation is. So as per Galilean transformation, the velocity, of course, is Galilean variant. In fact, all of us had studied, say at school level, relative velocity problems. For example, we write VAB, velocity of A with respect to B vector, equal VA minus vector VV. And where does this formula come from? This formula comes from this Galilean transformation. So, but acceleration will be Galilean invariant, as one knows, and therefore force will also be Galilean invariant. But the problem is, in Galilean relativity, the space and time, they are different entities. They are not merging into one another. They maintain separate identity. Whereas when you demand the principle, the constancy of speed of light, you are forced to intermix space and time. So what happens is this: intermixing of space and time will, of course, will give rise to a different set of transformation formula for the coordinates of particle. And in the slide out here, I have written down the generalized Lorentz transformation equation. I have not assumed that speed is of the moving frame, or velocity of the moving frame is along x-axis. It could be along any direction. And the general transformation formula comes out to be as shown in the slide. Of course, if we set Vy and Vz equal 0 in this formula, we get back our original well-known formula: x dash equal gamma times x minus vt, y dash equal y, z dash equal z, and t dash equal gamma times t minus vx upon c square. So where gamma is Lorentz factor, 1 upon square root of 1 minus v square c square, were written out there. So all these are well known. Probably students may not have seen this generalized Lorentz transformation equation. So I thought it necessary to write it down. Now, all said and done, let us not forget that our velocity addition law, which originates from the Galilean transformation formula, is pretty good for velocity ranges much less than speed of light. It gives us excellent result. So our Lorentz transformation formula should be such that in the limit v by c, c being speed of light, much less than 1, should reduce to Galilean transformation formula, which it does. And one more important thing, the constancy of speed of light says that if one observer in an inertial frame sees the speed of light as c, another observer in yet another inertial frame will also see the speed c. So suppose at the origin of one of the inertial frames you have a source, a spherically symmetric source, sending disturbance in all directions. Wavefront is therefore spherical. So another observer who is moving with speed v, say along x-axis, will also see the wavefront spherical, neither elliptical nor hyperboloid or ellipsoid or hyperboloid or anything. Because if he sees the wavefront to be ellipsoid or hyperboloid, then he immediately identifies that we are the equivalence of the inertial frames is then lost. So in order that the speed of light remains constant.
Sir, sorry to
Hello?
interrupt you. Sir, please,
Yeah.
1 second. Sir, which number slide are you on? Because you did not say next slide.
No, I did not say next slide. I have not yet gone to fourth slide. So it is still the third slide.
Okay.
Right?
So, sir, we are moving along with your instruction. When you say
Yeah,
slide,
whenever I would require, I would request you to go over to the other slide, right?
Thank you so much, sir.
Right. So coming back to what I was saying, that speed of light has a very different designation. Add any speed to speed of light should give you back the same speed. So this Lorentz transformation formula should give us such a velocity addition law where adding c to v should get back c. So indeed we do get back all this. Therefore, the Lorentz transformation formula on the face of it seems to be most appropriate. Why the transformation formula should be linear in x and space variable and time, I will discuss that a little later towards the end of the talk. Now we go to the fourth slide, that is the next slide, where I had put the Lorentz transformation in terms of the matrices. L inverse, which one sees in the a 4x4 matrix, of course, this corresponds to the direct Lorentz transformation. And L, which one sees, again a 4x4 matrix, corresponds to the reverse Lorentz transformation. Direct means one has a particle with coordinates x, y, z with respect to observer O, and we have observer O dash with respect to whom the coordinates of the particles are x dash, y dash, z dash. So direct transformation relates x dash, y dash, z dash, t dash with x, y, z, t. Now please note here that T also is being treated at par with space coordinates, spatial coordinates. So T has no separate identity as in Galilean transformation. That is why in relativity, space and time, they are not two different entities. They merge into a single entity, become space hyphen time, space time. So as I said, L inverse is the matrix of transformation for the direct transformation, and this one, the other one, L, is the matrix of transformation for the reverse one, where you go from x dash, y dash, z dash, t dash to x, y, z, t. With this, we go to next slide, which is slide number 5. Slide number 5. Hello.
Sir, would you like to answer a small question on this slide which you showed?
Fourth.
The one which you were, Sir, one student asks that in y and z dash transformation, what is A?
What is?
A.
A meaning? A
so
means?
the symbol A. See the symbol A.
There is no symbol like A out here.
So I think the student has misunderstood. So I request the students to pose questions after careful observation of the slides. Thank you, sir.
It was on third slide. It was on third slide, I think.
It was on one slide earlier. One slide earlier.
One slide earlier.
Yes, sir. The y dash and the z dash transformation. Yeah, here. Yes.
Yeah. Oh, that was, I think, it is, it should be, is gamma. I think it should be gamma because one sees, you see, I sometimes while typing, some kind of thing occurs. Like you in the first equation, you see that x dash. If you look at x dash, you have in the last term gamma gamma vxt, right? I think the
Yes.
student can see that. So it is very easy to therefore conjecture, or indeed it would be that ये a तो कुछ है ही नहीं, ट्रांसफॉर्मेशन में तो a आता ही नहीं, तो this is gamma, and the symmetry of the transformation in fact demands that it should be gamma.
Yes, sir. It
So
is clear now. It is gamma. Thank you so much,
it
sir. We
is
can
gamma.
proceed.
Gamma meaning Lorentz factor, which is 1 upon square root of 1 minus v square c square.
Yes, sir. We continue. Thank you, sir.
Right. All right. Now I give a slight idea about the covariant contravariant tensor. First of all, what exactly is tensor? Students out here probably would, many of them may not have opted for the mathematical physics, so may not be knowing what exactly tensors are. Can I digress a bit and give a little introduction of what tensors are? Do I have the permission? Hello?
Sir, please go ahead. It is a very important topic and the students must be introduced to it.
Okay.
Yes, sir.
Very
Please,
good.
please.
Very
Thank
good.
you.
Very good. I give a kind of heuristic kind of definition, explanation of what tensor is, right? Suppose I have a certain property, or let me put it this way: the whole universe is a game of probe and response. I have a system, I put a probe in it, system would respond. One such example is, say, dielectric polarization. I apply external electric field, and dielectric would respond, and the response will be polarization. And of course, polarization vector is total dipole moment induced per unit volume, etc. One knows. But at molecular level, polarization is molecular polarization is proportional to the external field applied, as we all know. Now, proportional to external field, so molecular polarization is equal then some scalar alpha, some constant of proportionality times external field. And external polarization is vector. External electric field is vector. Alpha is called the polarizability, and this innocuously appears as scalar. Now, electric field has components Ex, Ey, Ez. Polarization vector also has components Px, Py, Pz. So I shall have, if I have some kind of an isotropy, let us say, then Px will be alpha x, Ex, Py will be alpha y, Ey, similarly Pz will be alpha z, Ez. So what is happening here is field in the x direction, which is probe, polarization is the response. So field in the x direction eliciting a response only in the x direction. And your alpha is the constant of proportionality. But physically, if one thinks that why should it not so happen that Other field components, for example, EY and EZ, they also will have some influence on the PX. So in that event, if that logic seems to be perfect. So in that event, I would write Px as alpha xx Ex plus alpha xy Ey alpha xz Ez. And similarly, Py equal alpha yx Ex, alpha Ey, and so on. So in this manner, what we are doing, we are not really sort of ignoring the effect of components like Y and Z, field components like Y and Z on the xth component of the polarization. We are considering entire effect into our consideration. So now if I write out mathematically polarization as a column vector, the Px, Py, Pz, and electric field component also as a column vector Ex, Ey, Ez, one can easily see what would be the relation. Column vector Px, Py, Pz is alpha times column vector Ex, Ey, Ez. Now, Px, Py, Pz is a column vector with, it is 1 cross 3 matrix. Sorry, 3 cross 1 matrix. And electric field also Ex, Ey, Ez, a 3 cross 1 matrix, 3 rows, 1 column. So alpha mathematically, suppose if happens to be a 3 cross 3 matrix, matrix multiplication is still valid. You have a 3 cross 1 matrix on the left hand side, 3 rows, 1 column, and equal product of 3 cross 3 matrix and another 3 cross 1 matrix. So you are getting, after taking product, a 3 cross 1 matrix equal 3 cross 1 matrix. So in this manner, one sees that if one extends the definition of alpha, polarizability, it no more remains a scalar. It becomes a quantity with 9 components and whose matrix representation is 3 cross 3. And such quantities are called tensors. In fact, in non-relativistic mechanics, the tensors could have 3 to the power n components, where n is the rank of tensor. This is a second rank tensor. So I believe in an approximate fashion, in a hand-waving fashion, what is the concept of tensor? I would say, if someone asks me, well, tensor is a quantity, is an object which has a matrix representation, and it relates one vector to another. Of course, if you go a bit deeper, you would find that as vectors satisfy certain rules of coordinate transformation, so do tensors also need to satisfy certain rules of coordinate transformation. Now, I believe with this a makeshift kind of definition, some idea of tensor is has gone in down the throat of the students. So we now go over to what exactly are covariant and contravariant tensors. You see, when I write a vector, whether I choose a three-dimensional Euclidean space or n-dimensional space, flat space, let us say, no curved one. We are not into discussing here Christoffel symbols and all such things. So contravariant components could be written as I have shown in this slide, as superscripts. I have a n-dimensional vector u, and their n components are shown with superscripts u1, u2, and un. And there are orthogonal vectors, not necessarily unit vectors. They must be independent and orthogonal vectors, r1, r2, r3, rn. These r1, r2, r3, and so on up to rn, they are called basis vectors. In a vector, if you write down a vector in full length, what would you write? Vector A equal A1 I cap, A2 J cap, A3 K cap, I cap, J cap, K cap are the basis vectors which have representation in three-dimensional Euclidean space as 1, 0, 0, 0, 1, 0, 0, 0, 1, and the components A1, A2, A3. So out here also I am writing vector U as UI, Ri are the basis vectors, like IJK are independent and orthogonal. Similarly, R1, R2, R3 up to Rn are also independent and orthogonal, but of course, they need not be unit vector. Those vectors which where components are shown with superscript are called contravariant. I'm shortly giving the justification why they are so called. On the other hand, those vector components where the components are described by giving subscripts u1, u2, u3, un, they are called covariant components. I have written it down. A relevant question is, why do we have this classification? The answer is, if the coordinate basis vectors are scaled up by any scaling factor zeta, then covariant components will get smaller by zeta. Sorry, contravariant components will get smaller by zeta, and covariant components will get scaled up by zeta. So since covariant component gets scaled up by zeta upon scaling up the coordinate basis by factor zeta, so the name covariance gets attached. On the other hand, contravariant component gets smaller by factor zeta upon scaling up by factor zeta the coordinate basis. The name contravariant seems appropriate. To make this idea a little more clear, we can go to I have R1, R2, R3 with subscripts as usual basis vectors, which are mutually orthogonal, and they are not necessarily unit vector. I can also define reciprocal basis vector. This we define, V here stands for the volume of the parallelepiped, R1 dot R2 cross R3. Everybody knows it. So the basis vectors, which are called reciprocal basis vectors, are defined in the manner as we can see in the 6th slide. Please go to 6th slide. Please go to 6th slide, next one.
Yes, sir.
Yes, sir. It takes a minute to share and be visible to all. Just a sec. Yes.
Yeah. So just see this reciprocal basis vector. We have introduced this vector while teaching our solid state physics. I think those who are the student here mostly BSc pass out, or they are in final year, so they have studied solid state physics already. So this concept of reciprocal basis vector is clear to them. One can see, suppose I scale up the R1, R2, R3 with subscripts by a factor zeta. So let's take R1 with superscript first, which is equal R2 vector cross R3 divided by V. If R2 is scaled up by factor zeta, R3 is also scaled up by factor zeta, V, which is volume of the parallelepiped, which is R dot, R1 dot, R2 cross R3, that will get scaled up by factor zeta cube. So zeta square upon zeta cube will give you 1 by zeta. So R with a superscript, as one can very clearly see, is scaling in the opposite sense. So the name of covariance and contravariance, why such kind of nomenclature has been made. Mind you, I again repeat, for contravariant components, I would write superscript, and for covariant components, I would write subscripts. I believe, yes?
Sir, there is a small question from a student. How covariant vector is scaled up by zeta?
Suppose I do it. Suppose zeta could be 1, 2, 3, anything, any numerical factor. If I do that, then the contravariant basis vector, reciprocal basis vector, that is getting scaled down by factor zeta. I here am giving justification of the nomenclature.
Yes.
Covariant meaning if you scaling up the basis vector, the component also will have to see, vector has to remain no matter whichever way you write, but the vector has to remain the same. So if you are writing, please go back to the 5th slide, the slide before. I have a vector u, contravariant component is ui, and basis vector is ri. So as just now I have seen that contravariance implies what? Scaling down by factor zeta, and covariance implies scaling up by factor zeta. So don't you see that in the 3rd line of this slide, vector u, आप zeta से अगर r को बढ़ाया जाए तो ये जो कॉन्ट्रावेरिएंट कंपोनेंट है जीटा से घट गया, तो जीटा जीटा कट गया, तो वेक्टर अनचेंज रहा ना
सर?
क्या?
Sir, I think there are people coming from South India also in your audience.
Okay.
So there are people coming from down south.
Language. Okay,
So
language. Yeah, sure.
Yeah, for those students who are from southern part of
India. I understand. So what I'm saying is, you scale up Ri, I subscript with factor zeta, which could be any scalar, real number. Contravariant component u superscript ui component will get scaled down by factor zeta. So you have a zeta in the denominator, you have a zeta in the numerator. The two zetas would get cancelled, vector remains unchanged. So in this kind of representation, you have, and one more thing, we shall, of course, very religiously would observe in tensor calculus, and that is, if there is a repeated index, repeated twice, Einstein's summation convention is that you don't write this sigma. It is understandable that a repeated index, repeated twice, has to have summation over. Summation over, if the I is the repeated index and repeated twice, so I will have a summation over I. And this summation I need not show. This is called Einstein's summation convention, which I am going to use subsequently. This convention makes the otherwise complicated expressions involving tensorial objects rather elegant, aesthetically pleasant. That's all. The convention is not a very big thing. So I believe I have been able to, at least for students, justify why the name covariance, why the name contravariance. Covariance, subscript, contravariance, सुपरस्क्रिप्ट, ये चीज ख्याल रखना है. This one has to remember, and why this name is given, such kind of names are nomenclature given, is, I believe, clear. Is it clear? I'm asking a question.
Just a second, I've been reading the chat box. Yes, sir, it is clear according to the...
Clear to everybody?
Yes, sir. Yes, sir. One question is, can you please tell about the concept of why we are denoting superscript on contravariant and subscript on covariant tensors?
Oh, that of course is a matter of choice. That has got nothing to do with physics, nothing to do with any justification. One could equally have made a choice like all covariant thing. But then, historically speaking, first Cartesian tenses came, and we have been so very used to putting subscripts. So covariant being something which goes easily down with our intuition. All right, so subscript goes with covariance. A superscript or contravariance doesn't go so easily. So slightly, I would say, not non-intuitive, but slightly different. So let it be a superscript. That's how probably, I think. There is no rule that one can write the entire textbook of tensor calculus changing the convention. Nothing will happen. No equation will give any different meaning. I think I am clear.
Yes, sir. Another question is that the part where sir has related the electric field and polarization is not clear. The part where your good self has related the electric field and polarization.
Okay. I was referring to, I could have taken any example. Offhand, I had taken that example of dielectric polarization. Dielectric polarization mein hota kya hai? What happens in dielectric polarization? At molecular level, well, you apply an external field. Whatever is the effective field inside the dielectric? There would be some induced dipole moment. If molecule is not a dipole already, there will be an induced dipole moment. And if a molecule like H2O, which is already a dipole, so dipole moment will get enhanced. So enhancement in dipole moment or dipole moment induced is generally proportional to the effective electric field which is inside the dielectric, which is well known. I think at +2 level one studies all this. I'm sure at +2 level dielectric polarization is being taught. And
so there is a question, sir. How do we end up getting transformation matrix?
Oh, transformation matrix, which I showed in the earlier slide. Well, we write down, is that the question? Is that the question?
Sir, I'm just reading out the question directly from what the students are typing. So you can give an appropriate answer. We have a long journey. We have many lectures by you. So I would like to inform the students that here that sir would be with us for many days, not just one. So we can be clarifying our concepts slowly as classical dynamics lectures continue. So thank you, sir. Please continue.
This particular question, I believe I had not really written it down in the blackboard, writing all the expression, which is not possible here. So student is not following how the matrix comes about. But I can do one thing. Probably I can write out in a 5-6 steps, whatever required. Put it in a slide, in a set of slides, and give it to you. You can give whoever is asking, you can give that slide to him. He would understand.
Yes, sir. Thank you so much, sir. Agreed.
So we then all right. So we have explained covariance, contravariance, a slight digression. Of course, we don't need to really do so much about this. Now, suppose I have a particle, and well, I think I first take up a space-time diagram of a moving object. This is 9th slide. 9th slide. Yeah. In fact, one has to understand, if one understand what I'm saying here. Like, first thing is, an event is a point-like reality at a space-time location. Now, what is space-time? Space-time. Usually, we plot along x-axis, horizontal axis, x coordinate. If I want a 2-dimensional diagram, along horizontal axis, x coordinate, along vertical axis, time coordinate. And if I want a 3-dimensional diagram, then probably along say a line perpendicular to the plane of the paper, or in this case monitor, x-axis, horizontal one y-axis, and vertical one would be the time axis. So we just, because one cannot plot 4 dimensions anywhere, so I have to miss one spatial dimension. So in a 2-dimensional diagram, I would say 1 + 1, or in 3-dimensional diagram, I would say 2 + 1. 1 + 1 means 1 spatial coordinate, 1 time coordinate. 2 + 1 means 2 spatial coordinates, 1 time coordinate. So this is called either 2-dimensional, 1 + 1 dimensional, or 2 + 1 dimensional. This is called space-time diagram. So an event is a point like reality in a space-time location. That means suppose we are very familiar with space 2-dimensional diagram. Suppose we have along horizontal axis x coordinate, along vertical axis time coordinate, then any point in this plane is an event. Now, event must either be a first cause or embedded in a causal chain. Causal, the word causal means causation, means relation between cause and effect. First there is cause, then there is effect. As I said, first there is probe, then there is response. So any event or any point will be the first cause embedded in a causal chain, because that event will unleash a series of events, and that means a series of points in these space-time diagrams. So that is why I have written any event must either be first cause or embedded in a causal chain in which cause effect is propagating in unique direction through a series of events. If this is clear, because the language is slightly involved, probably to nubile minds of our teenagers, probably this may not be very clear. So in simple words, let me put it this way, that in space-time diagram, xt diagram, any point is an event. An event leads to further event. If you slap somebody, the other person will abuse you or slap you. So there would be unleashing of some unsavory events. So what I'm saying is an event unleashes a chain of events, and this is a causal chain. Every preceding event will be cause of the every subsequent event. Preceding event is the cause, subsequent event is the effect. So that is what I am trying to make clear. Second is time for us. What is time? This is a question bothering everybody. I'm sure I have so many erudite professors. If they are, I'm explaining such things to the in front of them. This is very audacious move of mine. But anyway, please condone me for this audacious act. Time, I consider, you may not agree with me, is simply a coordinate, like spatial coordinate. In relativity, time has no special meaning. It is one of the components of space-time combined entity. So I've written like these spatial coordinates as we understand from the theory of relativity. Specifically, different coordinate systems have different times for the same event, and transformation of time from one frame to another depends not only on time, because time is not constant, it has been mixed with space coordinates, so it will depend on spatial coordinates. And past, future, present, this concept is not an inherent property of time. Time does not have any flow. Flow which we associate with the concept of past, present, and future is basically a causal flow, which is a chain of event. You do an event, you do something which unleashes a series of events, a causal flow. That flows. Time does not flow. And this causal flow does not depend upon the reference frame. An observer or agent has knowledge of his past, which is collection of all events earlier happened in his life in his causal chain. The agent is acting in his present at the moment to have a causal effect on his future, which is further down his causal chain. And different observers are experiencing different causal chains, and there is no such thing as, because if I unleash, and even I am born today, my time t equals 0 is today. Unleashing of subsequent events will be my future. So there is no such thing as global past, present, future. So this 5 things, if we keep in mind, the philosophy of space-time diagram becomes little more clear. So we go to the 7th slide. As I say, motion of a particle can be seen as sequence of events which are points in space-time diagram. I've already explained. And we introduce now a 4 vector. 4 vector, why? Because we are living in as per relativity, living in 3 + 1 dimensions. So vectorial representation will be in the same fashion, in concurrence with that. So the 4 vector position vector in tensorial notation denoted by R mu. This is 7th slide. R mu. The time coordinate is CT. Just to make dimensionally same, C is multiplied. And R is 3 position vector. Matlab R is X I plus Y J plus Z K. We have a very nice notation. CT we denote, position vector usually is contravariant. So CT we put as the X0. And R, the position, the 3 position vector, X1, E1. X1 is component, E1 is the basis, X2 component, E2 basis, X3 component, E3 basis. X1 actually is X, X2 is Y, X3 is Z. In this manner, we have a kind of notation which looks very elegant and manageable, because as we proceed in tensor calculus and in general related towards Einstein's equation, etc., things become very complicated. So we should have right in the beginning devise some kind of notation to write everything in shorthand. Now, square time interval is R mu covariant, R mu contravariant. And this is equal eta mu nu, R mu, R nu. Eta mu nu is called, it is a symmetric tensor of 2nd rank, and it has diagonal elements as 1, -1, -1, -1, and all off diagonal elements are 0. This is called metric of Minkowski space, or simply Minkowski metric. Now, what exactly is metric? Metric, as I understand it, let me explain it to the students. Suppose I have a Euclidean flat space and I need to find distance between 2 points. Points have the coordinates x1, points have the coordinates x1, x2, x3, and let's say something like y1, y2, y3. Here x is the x1, x2, x3, the 3 coordinates of one point, and y1, y2, y3 are the 3 coordinates of another point. If I apply simple coordinate geometry distance, geometric distance formula, I would get d square as how much? X1 minus y1 whole square plus x2 minus y2 whole square plus x3 minus y3 whole square. Here, physical distance and geometric distance, space being flat, will coincide. On the other hand, think of a curved space. A curved space, say curved space of the earth. You want to join point A on the surface of the earth to point B. Draw a line underneath the earth. You get the geometric distance. But take a line through the surface of the earth, which is actually going to be an arc. That would be the physical distance. So physical distance for a curved surface is never same as the geometric distance. And this metric takes care of the relationship between the physical, or it describes the physical distance, not the geometric distance. Particularly for flat space, the metric, you have ds square equal for flat space, dx square, dy plus dy square plus dz square. So here, if you wish to write in matrix form, you may write your metric as a Kronecker delta, delta ij. It would be written as delta ij, delta x I, delta x j. You see, delta ij has the property that when I equal j, it's 1. When I not equal j, it is 0. So you get all diagonal elements dx square plus dy square plus dz square. This is the story, or 1, 1, 1, 1. This is the story with Euclidean flat space. Minkowski space is not like Euclidean space. Here I have seen the quantity r square, which is actually how much? It is actually r0 square minus r1 square minus r2 square minus r3 square. You may say, where has it come from? It has come from the fact, I think right at the beginning I have mentioned that all inertial frames are equivalent. So at the frame at rest, there you have a source which is spherically symmetric, emitting light. Wavefront is sphere, and sphere has equation x square plus y square plus z square equal r square, and this for all inertial frames will appear as sphere only. That means r square minus x square minus y square minus z square equals 0, which remains invariant. So from there it has come to us that the square of the space-time length is invariant. And matrix, how have we picked up the metric? As I wrote, r square equal minus dx square minus dy square minus dz square. So diagonal elements will be 1 minus 1 minus 1 minus 1 is but a foregone conclusion, and off diagonal elements will be 0. I believe this point of mine is clear. the Minkowski space of our special theory of relativity has a different metric. Its metric is not that of Euclidean flat space. Euclidean flat space has Kronecker delta as its metric, which is only 1111, diagonal 1111 for four-dimensional space, of diagonal elements 0. Therefore, space-time diagrams has lot of complications, lot of difference from usual space diagram. I have given two problems after that. For example, for velocity, gamma and gamma beta. Beta is b by c, and gamma is 1 upon 1 minus b square root. This is a four vector given by Minkowski metric tensor, 1 equal eta mu nu u mu u nu. This is very easy to show. I have shown it in the next slide, that is slide number 8. Please get to the next slide. Next slide. The object eta mu nu u mu u nu is, in terms of matrix multiplication, it could be written as, say, some m equal a 1 cross 4 matrix, gamma beta x, gamma beta y, gamma beta z. As I said, your quantity which you want to show as four vector is gamma beta. Beta is a 3 vector. So 3 vector has components beta x, beta y, beta z. So you have gamma beta x, gamma beta y, gamma beta z, and this is a 4 cross 4 matrix. 1, minus 1, minus 1, minus 1 are the diagonal elements, and all off diagonal elements are 0. And for matrix multiplication to be conformal, because you have u mu u nu, you have transpose of this 1 cross 4 matrix, which is actually 4 cross 1 matrix, and you simply multiply this matrix, you would just get 1 which is greater than 0. So the problem that I have given is not a very big issue. Multiplication is matrix multiplication. The reason is your metric is a matrix. So, and the components of the vectors are also either column vector or row vector. Therefore, if such problems are asked, getting the solution boils down to simply a matrix multiplication. So I said, because this was for velocity u mu, which had, as you saw in the previous slide, components, the time component, 0th component, gamma, and the 3 components are gamma beta. Beta is, of course, beta x, beta y, beta z. So there are 4 components. So this 4 velocity, which could be written as dx mu d tau, of course, tau is proper time, I'm coming to that, is a space-like vector. Any vector whose dot, you see, in the Minkowski space, are you able to notice r square, r mu equal eta mu nu, r nu, you, and with eta mu nu diagonal, all this, you are able to notice that the dot product, r square basically, or r mu is dot product, basically is not dx square, dx0 square plus dx1 square plus dx2 square plus dx3 square as in flat space. It is the dot product is carried out differently. It is dx0 square minus dx1 square minus dx2 square minus dx3 square because of the invariance of the square of this quantity, the arc length. And so coming back to the 8th, I say that in fact, in 7th only I have mentioned that in contrast to a square space, sorry, go to 7th please, earlier one. In contrast, go to the earlier one, 7th please. In contrast to a squared space interval, which is always positive, the squared space-time interval could be positive, 0 or negative. Your squared space-time interval becomes effectively dx0 square minus dx1 square minus dx2 square minus dx3 square, unlike your Euclidean space dot product where you have dx1 0 square plus dx1 square plus dx2 square plus dx3 square. So Euclidean dot space vector dot product always is positive. On the other hand, Minkowskian space dot product could be positive because as well as negative or 0. That is what I have written here. In contrast to squared space-time in space interval, like your ordinary three-dimensional space, where squared space interval is always positive. The squared space-time interval could be positive, 0, negative. Positive is called time-like vector, 0, light-like, negative, space-like. So therefore, coming back to our problem, 8th slide, I can see that our M is 1. So in the solution to example, M is 1, which is greater than 0. So this 4 velocity is a space-like vector. Now, one more thing I need to tell you very explicitly, that choice of this metric, Minkowski metric, diagonal 1, minus 1, minus 1, minus 1 is not so sacrosanct. I could have made also a choice like minus 1, minus 1, minus 1, and then plus 1. Because even with that choice, one would have got square of the space-time interval invariant. So if that had been the choice, minus 1, 1, 1, 1, if that had been the choice, we would have had M negative. That is the 4 velocity time life. So a vector, a 4 vector would be space-like or time-like, depends on what you choose as your Minkowski metric. If you choose it to be diagonal 1, minus 1, minus 1, minus 1, as you see, 4 velocity is a space-like vector, and if you make the other choice, it becomes time-like. There is no hard and fast rule. So now we go to 9th, which I already have explained. Then with this, I'll make some remark. The diagram that we have explained, it requires making some remark. Lorentz transformation tells us that space-time Space and time are two aspects of same basic entity. They mix in different ways for different observer. Uh, Full stop. Sorry, there should have been capital W. Anyway, when gravitation is present, the whole of space-time bends, as one knows from Einstein's general theory of relativity. Such bent space-time are called Riemannian space-time. Space-time exists. Mind you, space hyphen time is a single entity. Space-time exists independently of all things. It is a container, a backdrop, a background for everything that happens. And even through coordinate systems which differ from observer to observer, the underlying entity, the space-time, is same and unique. Now, a pertinent question is, because I always try to give equal emphasis to mathematics as well as the physics part. So, to a conscientious student, a question can arise in one's mind that the Galilean space-time, which we are intuitively familiar with, how does it differ from Minkowski space-time? So Galilean space-time, of course, is a combination of our everyday space and everyday time. Unlike Minkowski space-time, where space and time are intertwined. So both space-times, the Minkowskian and Galilean, they are manifolds. That is, they are continuum set of points. Both have one space temporal, matlab time se related, and three spatial dimensions. Both manifolds have topology of the punctured sphere. This I don't need to explain. Topology is something we can relegate to back burner. Both manifolds are flat. Even Minkowski manifold, Minkowski continuum set of points is flat like Euclidean, free of any curvature. So in both cases, space-time is fundamental, unique, and absolute, and it remains always a background and the container of whatever things or events happen. So what is the central difference? Central difference between Minkowskian space and our ordinary space and time is only one, is that Minkowski space-time, in contrast to the Galilean case, mixes space and time. And the mixing, of course, because observer can have different speeds, mixing will be different for observers with different speeds. I believe this piece of physics is clear to everybody. I'm asking a question, in fact. Is it clear? Hello? Hello? Hello?
Yes, sir.
Yes, sir.
Whatever I said is clear to everybody.
Yes, sir.
Well,
Voices.
I don't expect. Unabashedly, I can share that it took me very long time to assimilate all these concepts. So it may not be clear in the first reading or first listening, but anyway, I had already requested Madam Punita to share everything with students, and I'll send for the students many problem set already I have sent, several problem set, several books which are presently not available, I will send. So student at the end of the day will feel that they, of course, if they work very hard, they will feel that well, we have understood something, right?
Yes, sir. Yes,
But
sir.
I think now I may crack take a little time, 2 minutes time, and crack a joke sort of a thing.
Yes, sir.
Do you mind? Do you
No,
do our
sir. No, sir.
no?
Please, no, sir.
Okay,
Please
okay,
continue.
okay,
Continue.
okay. I keep telling me, I keep telling me that you have to be a ghost of Sisyphus. Well, Sisyphus is a mythological Greek god. He was cursed by a greater god in their hierarchy to take a boulder up a hill. So Sisyphus was trying very hard, very hard. Uh, he takes the boulder few steps up, but the boulder ultimately will roll down. And he spent a lot of time, got terribly bored and exhausted. So the curse was such that he will have to accomplish this task, or else he will not be rescued. So what did Sisyphus do? Sisyphus trained his mind. He started telling himself that please enjoy the task. This is a boring task, maybe utterly boring, but keep enjoying this task. And if you enjoy, if you get those feel good, uh, what you call feel good hormones, then you will keep doing, and ultimately one day you would be able to succeed. So that is the story of Sisyphus. And in my life, I have I have learned a lot from this story. Keep on doing your work, never say die. Ultimately, one day, one fine morning, you will understand. So that's why the name, that I am a ghost of Sisyphus. I believe people have not been able to enjoy
No, no,
the.
sir, it is not like that. One cannot continuously listen to physics, and therefore one small joke in the middle is always a very welcome thing. That's
No,
really
but
nice.
actual the joke, I do not know. I have no expertise. Had I had that, of course, that would have been so much better. But this is not a joke at all. This is, in fact, a parable sort of thing. Anyway, so students at the age of 65, I have only one advice to our student, and in fact, I shared this with Madam Punita once, that in the world there are two castes in the entire world: fast learner and slow learner. Fast learners, of course, do not need teachers. A very little push is required. They would learn on their own. Slow learners require teacher, require a lot of time, require a lot of fortitude, require a lot of hard work, and more importantly, they ought to have patience of a vulture.
Very true,
Um,
sir. Very true.
and I am a slow learner, so I think I have patience of a vulture. Uh,
Indeed,
uh,
sir. Indeed. Indeed.
I believe patience. Why I'm relating patience with vulture? Everybody probably had appreciated. No,
Yes,
uh,
sir. Yes, sir.
everybody has.
Yes, sir.
Anyway, okay,
Only a
okay.
vulture has the patience to keep on watching extremely slowly and then
Yeah,
plan the
yeah.
entire way of capturing a prey. And therefore, the simile is just wonderful. Thank you, sir.
Yeah. In fact, there used to be. Let me go to him. Let me go. Hello.
Yes, sir. You are audible.
Audible.
Yes,
Yes,
sir.
perfectly
Yes, sir.
audible,
You're
sir.
audible, sir.
There used to be a movie in our time, Methanol's Gold, and Gregory Peck. He was a favorite of mine, a favorite actor of mine. He acted in Methanol's Gold, and there was one scene from there. I learned this, that one ought to have patience of vulture. Anyway, so jokes apart, let's come to space-time diagram.
Sir, excuse me, sir. I'm sorry for
Ah,
interrupting you. There
ah.
is an announcement for the student that students are requested to ask their queries related to the lecture in the question answer box. And it is just on the bottom. So please
Acha.
ask your queries related to the questions to the question answer box only. And other rest of
In the
queries.
chat box. In the chat box.
No, no.
Chat box.
Sir,
Okay.
question answer box. Question answer box.
Question answer box. Where is question answer box?
So there is the option of Q and A
Q
at
and
the
A.
bottom where you have the control for mute and stop video.
Mute and stop video and then share. Then share participants and more. More may chat, raise hand,
Yes.
hide my video, hide non-video participants, show name when participants join, and disconnect audio. But this is all that I have. But anyway, you
No,
can tell
sir.
me the question.
Okay, sir. I will read it for you one by one.
Ah.
Sir, first question is there any physical quantities that not belong to contravariant and covariant?
Any physical quantity.
Am I clear, sir?
Question is clear. Well, see, physical quantities could be classified into scalar, vector, and tensors. So concept of covariance, contravariance come in the case of vector. Vector, of course, is a tensor of rank 1. You can say so. So question of vector, contravariance, covariance comes in the case of vector and tensors. And scalar quantities are scalar invariant. They are neither covariant nor contravariant. That's the simple answer. I think I'm clear.
Okay, sir. Okay, sir. Second question is from Roshan. He is asking, you said time is a coordinate, which means it will have a fixed point with respect to some other point, similar to position coordinates. Can we go backward and forward with respect to a fixed position in position coordinates? Is it possible with time as well? And can we go back and forth a fixed point in time?
See, fact is, our intuition is geared to look at space and time as two separate entities, which they are not. Once they have merged into one another, we really don't have, as I say, time has no flow. Only a point in the space-time diagram, right, is an event, and that event in somebody's life will unleash a chain of events. So you have a one line for that person. So entire space-time diagram will be crisscrossed with one lines, right? Not getting it.
It's okay, sir. We go to the next question. We'll have more time if they want further clarification. So the next question is from Arun Sheshadri. He asks, is the metric a transformation matrix from curved space to flat space?
Metric.
Is the
There are two
metric
things.
transformation, a transformation matrix from curved space to flat space?
Transformation matrix. Matrix. You mean array of numbers. Matrix meaning array of numbers.
Yes.
Transformation matrix from curved space to
flat space.
No, how could that be curved space? Actually,
Okay.
I think I have made it clear that I have only two flat spaces. One is Euclidean flat, जो plane geometry हम करते हुए आए हैं. The plane geometry we have been doing, right? Euclidean flat, three angles of a triangle equal and all that stuff. And another is our flat space, though, is the Minkowskian flat space. But then here, the two axes, let's say x-axis, which is along horizontal direction, time axis, they, for bodies moving with some velocity, get slightly smushed. And that leads to length contraction, time dilation, etc. Nevertheless, flat. And then we have curved surface. Curved surface is, of course, a very different story. The metric of the curved surface will not be constant. For example, metric of a black hole, that would be, it is called Schwarzschild metric. That, of course, is a very different metric, right? So what I want to say that there is no such transformation. The curved space is a very separate entity from a flat space is a very separate entity from a curved space.
Okay. So, sir, the next question is that possible to explain how space and time mixes in Minkowski space-time?
It is very easy to see. We actually, what happens is, people like us are to be blamed. We have not shown students through pointing fingers that, okay, look at Lorentz transformation. You have x equal gamma x minus vt. You have t dash equal gamma t minus vx upon c square, right? These are all well-known transformations, right? So here, with t you have presence of x, with x you have presence of t, correct? With x you have presence of t also in Galilean, but t is absolute in Galilean, whereas here t mixes with x. Look at the transformation formula itself, you get the answer. They are indeed getting mixed up. So you have a kind of mixing up of space and time, and they are churned up, and they give a single entity. Call it Ram, call it Sham, call it space time, whatever you feel like. But it to be understood is it is a mixed entity.
Sir, next question is how can we define tensor?
I think एक बच्चों वाला toy definition I have given. Such definition I will not write anywhere in any paper or in any textbook, if at all I write. I have said that tensor is an object. If you remember in the course of discussion of polarization of dielectric, I say tensor is an object which has matrix representation, and 3 cross 3, 4 cross 4, these tensors relate one 3 vector with another 3 vector, one 4 vector with another 4 vector. Way of looking at it is tensor is a kind of operator. Again, don't take my words very, very seriously. It is only understanding. Tensor is a kind of, because in quantum mechanics, you represent operator by matrix. So very wrongly, I am just lifting that idea, saying that tensor is a kind of operator which operates on certain vector, gives you yet another vector.
Yes,
But don't quote me, don't quote me. This is all understanding.
Yes, sir. Yes, sir. Sir, another person, Jay Kaushik, asks, my doubt is that in space-time diagram, is there no significance of the present time? Only past and future, and how matter evolved in this situation?
Oh,
please clarify.
Present has so much significance that whatever is going to happen down the causal chain of yours, your present determines that.
Okay. So next, sir, could you please explain the part of flat and curved space time in relation to Galilean and Minkowski space time?
Could you please explain flat and?
The part of flat and curved space time in relation to Galilean and Minkowski space time.
Okay, Galilean space and time, I should, because Galilean relativity regards space as a separate entity, time as yet another entity. So so-called Galilean space and time refers to only flat space, Euclidean flat. The Minkowski space-time, space-time, refers to flat space though, but as I said, observers moving with speed, say less than speed of light, the space will get somewhat smushed, and length contraction, that could be explained. I have not explained. Length contraction, time dilation, everything is a consequence of smushing of this. So flat space, Galilean or Euclidean, Galilean goes to Euclidean, or vice versa. The Minkowski metric also is a flat space. I have not discussed curved space, and I don't need to discuss. Reason being, presence of gravitation is not in our syllabus. For the ABC students who studies general theory of relativity, where the gravitation is present, the space then bends. I explained there is bending. Then you have curved space. You start with the derivative, shape of the derivative would change. Here, such derivatives are called covariant derivatives, and covariant derivatives will have all those Christoffel symbols and all, so much of complications. I have not discussed curved space.
Okay. Sir, can the speaker advise a book to study tensors for undergraduates?
Yes, I will. देखिए, मैं अपनी बुक की तो बात, I don't, I have written a book on mathematical physics. One chapter is devoted on tensors out there, but that is written much, say 10, 15 years back. So there are very, very good books. I have a couple of them. I will send them to Madam Punita, and she would
Yes.
Forward such books to
Yes.
whoever require.
Yes, sir. So, sir, just for a fraction of a minute, I just announce again that all the students who are attending this course, please remember that the whole course has been designed for you. Therefore, we have made arrangements for you to get study material, recommendation of books, all kinds of material which can help you in every way. And as the classes proceed, we shall announce all that. Sir, should we continue with question answer session, or you would kindly continue?
One thing I want to add that
Yes, sir.
I have today only discussed theory. The student should not get an idea that theory will only be discussed. We are going to do lot of problems.
Yes.
We have
Yes.
lot of books, lot of problems. In fact, one small problem set I have already given to you. So,
Yes.
but there would be an entire book. I will give 2-3 such books.
Yes,
And one book of classic, I think I have told you, is Rindler's book, Wolfgang Rindler, Relativity.
yes, sir.
There one has lot of classic problems, so that could also be given to the students.
Yes, sir. All the books provided, suggested by the speakers would be given to all the persons who are attending this particular course.
And problems will also be solved.
Yes,
Ki
exactly.
book de diya,
Yes. Yes, sir,
problems will
exactly.
be solved.
Exactly. So we will be solving the problems with each speaker for each subject. We continue. This is just the first day. I'm sure within few days they would come to know what we have planned for them. And I'm sure nobody would go back unhappy at the end of it. So should I continue with questions, or would you like to continue with your lecture? What would you like? Should I continue? 3 questions are left.
Ask the students. I think, are they fed up, or I can teach for a couple of hours more. I don't mind.
Sir, let us first finish 2-3 questions which are still there with us, and then by
Right,
the
right.
time the students will answer whether they would like to continue or not.
Right,
So,
right.
so the next question is Minkowski space-time equivalent to Riemannian space-time? If not,
No, I said when
not, yeah,
gravitation is present, space bends. It's called Riemannian manifold. I think I have already mentioned that.
yes, yes. Then is it so that Minkowski's ST transforms to Riemannian ST while going from STR to GTR? Please
Yeah,
clarify how they
exactly.
differ.
First thing is, in STR we have only inertial frames. GTR also talks about non-inertial frames. Number one, and number two, here we have no gravitation. There you have gravitation, and which bends the space.
So next question is, what is the physical significance of tensor?
Tensor, oh, very good question. I would love to answer this question. And in a very colloquial, very intuitive fashion. See, whoever has asked, I'm referring to that student only. Well, he is, of course, in the state of evolution. All of us are in the state of evolution. So whatever he is at the moment, he has not been come thus far only through parental influence. There had been peer influence. There have been influences due to social media, these days, whatever you have. So whatever he is in fact in a rough way of looking at it, is a superposition of the influences like parental influence, like peer influence, like influence of social media, like influence of the environment, and all such things.
The next
So,
question is, oh, sorry.
so no. I mean, not yet finished. So, in the case of tensor, writing that, say, come back to this example of polarization of dielectric. Polarization along x direction px should only depend on x and should be bereft of the influence of Ey and Ez, only depend on Ex, is a very uh, untenable proposition. I think everyone appreciates it. Why should EX only influence PX? Why so much of partiality? EY, EZ can also influence PX. And similarly, PY can be influenced, polarization, by all three, EX, EY, EZ, like parental influence, like social media influence. Are you following? So in the process, what one has is PX equal some proportionality constant alpha XX EX, alpha XY EY, alpha XZ EZ. So PX, PY, PZ is a column vector, EX, EY, EZ is a column vector. Both are the 3 cross 1 matrices, and in between वो जो alpha x, alpha xy, alpha xz, ये 3 cross 3 matrix हो गया. So tensor actually is relating one vector with another, and it is why physically I go in for tensor, for the simple reason that why should the polarization component, for example, get influenced by electric field X component? Y and Z component should also influence. Guided by this spirit, I introduce tensor as I look at it.
Okay, sir. So next question is, how can we
has the student understood what I'm trying to?
By the time the answer comes, we can take another question, because they will have to write. And Anu Krishnan, please write in chat box whether you have understood the answer or not. So by the time the answer will come, we can take next question. If he still has any problem, we will discuss again tomorrow.
Right.
How can we distinguish an event as a cause or an effect? Is it dependent on an observer?
An event
as a cause or an effect, is it dependent on observer?
Yeah. And actually, it is a question which has, you see, if I fire a pistol, a bullet will come out and it will hit a target. So coming out a bullet is the cause, and target being hit is the effect. Now, that's what observer on the ground sees. Fine. Now, observer who has not seen firing of the bullet sees that the target being hit, and with that target, suppose so many things were leaning against it and all things falling flat. So to him, target hit is the cause, and everything else which is leaning against it, falling flat, is the effect. So I feel that cause and effect are observer dependent.
Okay, sir. The next.
But this question is a very, very good question. I would think over it deeply and get the in the next session, if you allow me, I will explain probably in better detail.
Sir, the next question is the difference between the metric of Euclidean space and metric of Minkowski space-time. What is the difference between the two?
Euclidean space, flat Euclidean space, मैंने कहा ना कि वहाँ physical distance and geometric distance same. D square is x square plus y square plus z square. चलो आपने time भी कर दिया मान लो, तो c square plus t square t square. सारे plus sign हैं. So because of this plus sign, the metric will be diagonal 1, 1, 1, 1. Or off diagonal elements 0. It will be a 4 cross 4 matrix with all diagonal elements 1, off diagonal elements 0. or ऐसा, this kind of quantity is nothing but chronic. It is represented by our mathematical student, mathematical physics student know, is represented by even quantum mechanics students know. Kronecker delta symbol, delta ij. Delta ij is 1 for I equal j, and delta ij is 0 for I not equal j. So metric for Euclidean flat space is delta ij, Kronecker delta. Whereas for Minkowski space, since diagonal elements, as I have chosen, 1, -1, -1, -1, and of diagonal element 0, so this is not delta ij, this is something else.
Okay, so next question is, did Einstein come up with the idea of representing space and time as Minkowski space-time diagram?
No, 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 it was Hermann Minkowski. Well, in fact, he was teacher of Einstein.
Okay, okay, good. So another question is it correct to say that metric tensor of space-time tells how to measure distance in a particular space-time, inferring from the
Yeah, definitely. Metric tensor, in fact, as I say, black hole metric will give me entire property, event horizon, everything of black hole. In fact, metric tensor is the fundamental one of a given space-time. It gives all properties of space, whatever space-time we are under consideration. Of course, one has to appreciate this. Such a statement given in a hand waving manner is one thing. To appreciate this, of course, one has to study a bit. Then one will understand why metric is so important. Metric is so important.
Thank you, sir. The next question is it possible to explain mixing of space-time using some physical example instead of equation?
Physical example, I really not getting this question. Space-time, I think I have taken pains to get into the philosophy of it. It is just a backdrop. And mixing is necessitated as in the case of as in special relativity case, is because of negative result of the Michelson-Morley experiment, which led to the interpretation by Einstein that speed of light is constant in all inertial frame. So physics of, if you trace the origin of physics of this, so ultimately the origin lies in the negative result of Michelson-Morley experiment or principle of constancy of speed of light.
Yes, sir. Sir, the next question is, how the space-time is related to gravitational wave?
Gravitational wave, that is a separate, that is quantum field theory. We are not going to discuss that.
Okay.
But space-time, gravity present, mass present, that will give rise to bending in space-time, and metric will not remain Minkowskian. It will become, depending on what type of, as I said, for black hole, you have Schwarzschild metric. Anyone can type Google and in Google and get what shape, what kind of structure this metric has.
So next question is, as said, tensor are represented in matrix. Sir, do explain the difference in tensor and vector, as both can be represented in matrix form.
No, tensors are not really. I have worked with a tensor of second rank only, right? Yes, Either I have talked about three dimension space, spatial dimension. So you have 9 components as your polarizability tensor. 3 to the power 2, 3 to the power n is the number of components, right? So I have taken their tensor of rank 2, and for special theory of relativity, we need 4 vectors. So we have 4 to the power n components, and I have taken tensor of rank 2, 4 square, 16 components, right? Uh, but that doesn't mean I have tensor of rank 2 only, not beyond that. I have tensor of rank 3. For example, any student who has studied mathematical physics is well aware of the Levi-Civita tensor, which is tensor of rank 3. It has 27 components. Then student who has studied tensors, of course, in mathematical, are aware of the elastic coefficients, and compliance. All such things are tensor of rank 4 with 81 components. They cannot be represented in matrix form. So only second rank of tensor and first rank, of course, in column vector form, can be represented in matrix form. So tensor is something which goes far beyond a matrix representation. Matrix representation is a convenient one for second rank, first rank, and all that.
Sir, how do we really imagine more than 3 dimensions if they exist at all?
More than 3, I really not talking about 4th spatial dimension. Well, in string theory, one has 10 dimensions. 3 dimensions are spatial dimensions are there, and rest of them compactified. We are not doing all that. 4th dimension is our time, and the necessity of introducing time arose again. The root cause of everything is the constancy of speed of light.
Yes, sir.
Right?
Yes, sir. Yes, sir. Yes, sir. Another question is, sir,
fourth dimension, if student is asking कि 4 spatial dimension है, फिर क्या होगा? Then I would advise him, first let him think of some object just confined, incarcerated to live in 2 dimensions. 3 dimension उसके लिए क्या होगा? Let him come up with the 3rd dimension क्या होगा? वो उसमें क्या होगा? वो let him come up with some idea, then he can relate to our plight if there are 4 spatial dimensions.
Sir, how do we really imagine more than 3 dimensions if they exist at all? You can imagine. You have to then wait for statistical mechanics.
Imagine where spatial.
That's a question I'm saying. They've asked, how do we really imagine more than 3 dimensions if they exist at all? That's the question.
No, they don't exist. We live in 3-dimensional space. That is, and 4th-dimension time was more of a matter of necessity, and subsequently we realized, at least special theory of relativity is well-tested theory. There has never been so far any contradiction to it. So we are living in 3 plus 1 dimension. We never say 4. 3 plus 1 actually is the way to put it. And what is the boy asking?
That's all, sir. As far as imagination is concerned, then they have to wait for statistical mechanics.
Imagination.
You have to imagine
Of course. We of course have the concept of vector space, which could be finite dimension as well as infinite. The vector space concept, mathematical physics student again would have, they must have studied. So they know that imagination, of course, it could be, one can imagine n-dimensional space.
Yes. Sir, how to visualize the special theory of relativity to get better understanding of it?
How to visualize the entire theory to get a better understanding of it. You see, such theories, special theory of relativity, quantum theory, etc., are very non-intuitive. So, in a very general way, I would say that one has to jettison one's uh, intuitive ideas which one had nurtured since childhood. One should broaden one's mental horizon, and so that one can, accept things which otherwise a layman would say can never happen. It is a very general, because all whatever we are discussing are, as one appreciates, are very non-intuitive. Length contraction, non-intuitive. Time dilation, the paradox, the twin paradox, everything, so non-intuitive. So what is the way to appreciate all this? To broaden one's mental horizon, or what else one? I don't think there could be any other way.
Dr. Punita, I will suggest that Dr. Goswami can have a look at the question and answer section at the end of the talk and answer only questions related to his, lecture.
Yes.
Otherwise, it is an endless exercise. He will not be able to cover whatever concepts he wants to cover, and not all questions are really related to the talk.
Yes. Yes, sir. So, sir, at this point, we discontinue asking questions.
But then I just make a small note. Please don't mind. I beg to differ slightly. To me, students never ask stupid questions or unrelated questions.
Sir,
so
I shall type out all the questions and I shall pass on the file to you.
Modus operandi of giving them answer, providing them answer, you can devise. But
yes, sir.
Don't reject. Don't reject.
No. Sir, the entire
You can have a look.
Yes,
you
sir.
can have a look at the question.
Modus operandi you can devise.
Yes, sir. Sir, I shall forward all the questions in typed format to you, and you can then answer those questions which have not been answered yet. Sir, please continue.
Okay.
I think we should continue few slides more. If the speaker, if sir, you agree, and if you would like to teach few slides more, then we can continue. However, if you would like to continue the rest next day, that is tomorrow, it's up to you, sir. Please clarify.
I think. Let me share with you. My dog, he's very para to me. He's patiently waiting. Now I will have to take him out.
Okay, sir. Okay, sir. So, sir,
he's like my son. He's like.
Yes, sir. So, sir, we stop at this particular slide. However, in the next lecture, we shall continue with this slide onwards. And at this time, I would like to now give few announcements to the students and clarify a few things, because the students are continuously asking in the chat box, and they're asking several things. Although I have clarified twice, but I think it is required again.
हाँ, इनको आप मेरा एक हम्बल ये वो है, फिर से रेपिटेटिव में भी, कि इनको कहिए कि प्रॉब्लम्स खूब होंगे, बहुत होंगे. आप क्योंकि स्टूडेंट्स यहाँ प्रॉब्लम के लिए आते हैं, मेनली इनका दिमाग रहता है प्रॉब्लम की ओर.
जी सर, definitely. So, sir, the announcements, I would take your permission to give announcements to make announcements.
मैं फिर चलूं? Shall I leave?
Sir, if you decide not to continue with the lecture now, but tomorrow when we meet again in the evening, I would now
tomorrow
like to,
at 5 o'clock, 5 o'clock, or maybe you can start at 4:30 if the suits it, if it suits
yes, sir.
everybody.
Yes, sir. Yes, sir. Yes, sir.
आप मुझे बता देना.
Yes, sir. Yes, sir.
Doesn't matter.
So we all, we at NASI, as well as the NASI Delhi chapter members, as well as the students, all of them who have connected to us through Zoom platform or through YouTube link and are watching, have been listening to this lecture. I'm extremely, from their side, I'm extremely thankful to Professor Partha Goswami for giving us this wonderful, enlightening introduction starting on classical dynamics. And I thought the senior amongst the college teachers should initiate our talk, and classical dynamics is required as some students do have examination coming in. I therefore thank you a lot, sir, and I'm extremely grateful to you
My
for
pleasure.
your
My
agreement,
pleasure.
for your
Thank you
consent.
very much.
And I look at this opportunity as a lifelong opportunity to connect with hundreds and thousands of students, to impart knowledge to them through experts like you and all others who will be joining us in this initiative. Thank you very much.
Please keep. I'll be retiring in few months. Keep giving me opportunity. I would
Sir,
love to.
Sir, a teacher.
It is my payback time. I shared with Professor Khattak that the university or students have given me a lot. It is my payback time.
Sir, a teacher retires only when he leaves the world. Till the last breath, till the last day, the teacher is always imparting knowledge. And therefore, I differ in thinking that the teacher ever retires. The teacher never retires. So,
Sure.
and I'm also extremely thankful to the other panelists who have been with us, Professor Annapurni, Professor Khattak, Professor uh, uh, Professor Samit Mandal, who have also joined us. They are going to give lectures later in the series of talks. And for the students, the announcement is the following: we please don't panic. We have arranged detailed classrooms for you. In those Google Classrooms, you'll be able to join, and for each subject, a separate Google Classroom has been connected, and it is available and it is being readied for you. So as many subjects, as many classrooms, you'll be able to become part of it. You'll get entire study material, recommendation of books, ladder of books, which book to study first, which book to study after that, books for recommendation for numericals, material for practice, several numerical solved ones, unsolved ones. As much as we all teachers can collect for you and recommend and suggest you, we all are going to give you that completely for your use. And therefore it will be an enriching thing, an enriching journey also for a person like me. I have started this course because I want to revise my physics. It's been 25 years I gave NET examination, and that was the last time when I was touching each subject. So as a teacher also, I'm learning from all professors who will be teaching this section. So I'm a student also along with you. So every study material will be available. Kindly don't ask this again and again. It will be available to all, one and all. Everybody can take it, material, books, and everything. Number two, I would like to point out that again, that the first 2 weeks are covering classical dynamics of the BSc level, statistical mechanics of the BSc level, and electromagnetic theory of the BSc level, where we have, apart from Professor Partha Goswami, Dr. Gitanjali Sethi from Stephens College, Dr. Sanjay Kumar from Stephens College, then we have along with us Dr. Rashna Kumar from my college, and so on. The detailed timetable with our basis will be given to you in the respective Telegram links, or any way in which we are contacting you, either email or Telegram link. So kindly do not ask these questions again and again. We are taking care of everything. Today was the first day. I apologize if there was any mistake, any lacuna, any delay in any particular thing. This is a huge mega event, and if we could do whatever we can, we have done it. And I hope you take it in the correct perspective, as it is a service to the nation, a service to the students, a service to science, and a service to physics, and my way and my team's way of helping you all. I request Dr. Poonam to just flash out the PPT or the slide, which I would like to thank. And I must tell you, the source of inspiration are the alumni students of my own college who have left my college. However, they have decided to persist in physics, and it is my pledge to help them in every way. And because of their inspiration, I've started and have got the courage to start this mega event. So next slide, please. So along with myself and Dr. Pushpa Vindal, who is a co-convener, We have a team of members, and I would like to mention again that if my alumni had not helped me with the basic work, I would not have been able to do this at all. Next slide, please. So the organizing committee at present is including Dr. Poonam Jain from Sri Aurobindo College, Dr. Tiranjita Srivastava from my college, Dr. Yogesh Kumar from Deshbandhu College, Dr. Neetu from Daulat Ram, Mrs. Barsha from my college, and the students who have been helping me since beginning is Madhuri Ganguly, Mohinit Kaur, and Himashi Mailawat, and at least 20 more whose photographs I do not have right now. I thank you all. And this was the announcement. If there are still any queries, the students are kindly requested to post it on the email, post it on the Telegram link, and it will all be attended to. With these words, I think we come to a close of today's session, and we would continue every day, and we would like to make it as smooth and as enjoyable and as learnable as possible. Thank you so much, sir. Sir,
I'm sorry.
thank you so much, sir.
Thank you.
Professor Annapurni, yes, thank you so much, sir. Professor
Yes.
Annapurni, we would like to hear your sweet voice blessing us all. As you are also a senior person.
That's a nice arrangement you have made, Punita, and I should really appreciate Pushpa Bindal, Yogesh, and Punita for organizing this, because I know it's very difficult to do it, and I think you have initiated it, and I hope that this goes on very well.
Yes, indeed, ma'am, with your blessings.
Yes,
So,
sure.
Indeed, ma'am, with your blessings. And Professor Khattak, I think the last word is always the best word. So we wind up today's work with a beautiful sentence from you. I have a beautiful sentence for you, sir, and I would like to say it. Do you allow me, sir?
Bolo.
So, sir, E is equal to MC square is what you keep on telling in thousands of your lectures, which I've heard thousands of times. And I have my own interpretation of it, which is quite funny. But if you listen it from the ears and you feel it from the heart of a student, it is a very dear one. So the consciousness of the physics community of India, the consciousness of the physics community of India, which includes everybody, teacher, student, learner, researcher, and everybody, to the power of square, that is C square. Consciousness of the physics community of India to the power of square multiplied by the mass of the physics learners in India and abroad. The mass of the physics learners of India and abroad, global, entire world, is equal to the energy given by Professor Ajoy Khattak sir. For teacher is equal to the energy given by the Professor Ajoy Khattak sir.
No.
Keep providing the energy to the teachers to propagate forward this legacy, what you have started, to keep on teaching and keep on learning and teaching. So the energy is that of Professor Khattak sir's initiative, which is equal to the mass of the body of the physics community multiplied by the consciousness, which strives us and forces us to work in all odd conditions. Whatever happens, we must go ahead, we must teach our students, and they must become knowledgeable like great persons like Meghnad Saha, Homi Bhabha, and so many more in our country. Thank you so much, sir.
Thank you.
Thank you, sir.
Good night.
Good night, sir.
Good night.
Thank you for everything. Thank you.
Thank
Really
you.
wonderful.
Ma'am, sorry to interrupt. Partha sir has raised his hand. I think he want to say
No.
something.
No. I did not.
Sir,
Actually, it was a mistake. By mistake. But anyway, good night to everybody.
Good night.
So we meet again tomorrow evening. Thank you so much, sir.
Right.
So, ma'am, with the permission of you and Pushpa Bindal, ma'am, and the respective professors available over here in this meeting, shall I end the meeting formally for everyone?
Yes. Thank you so much.
Thank you.
Thank you so much.
Thank you to all of you from my side. Thank you very much. A very good evening to all of you. Stay home, stay safe, or moreover, please stay connected. Thank you so much.
Thank you, Poonam. Thank you for having
sir.
it so well coordinating. Thank you, Yogeshwar. Thank you, everyone.
Thank you, sir. Thank you so much.
Thank you, Mandal sir.
Thank you. Good night.
Good night, sir.
Good night.